please, given that we will have this one, we won't be able to go around for the questions, so please repeat the question when there are
And
questions.
you have 3 scarves, and nobody so far given.
Okay. Yeah, for questions, you can give the scarves, up to 3 scarves when people ask questions.
Yeah, but the first is haven't done. This is mine?
I don't know. And is this waterproof there?
Yeah, I grabbed it myself.
Yeah, just do it.
Yeah, there's water down here. You want water? Or do you want to use it or something?
And keep an eye on, just keep an eye on, we have the signs for 10 minutes, 5 minutes, and out of time.
Okay. So out of time is completely out of time or time for questions?
No.
Out of time is completely out of time.
It's 40 minutes, including the questions, so that's how you...
It's not really much. So we have this one, the freshly charged.
Okay.
So we can use one of you, and the other one will have the.
Put that on your side.
Raz, jedna, raz, jedna, raz, dva, raz.
Yeah.
Did you forgive them?
No. There's eavesdropping, and they just heard us speaking like the batteries are dead, you know. Okay, so it's time.
Potom se zapne, jo? Má to mute, jo? Má to mute.
Unmute it.
Can you hear me okay?
Nebo potom víš ten, jo?
Higher up? Hello? More up? Hello? Can you hear me okay? Yeah? Can you guys hear me okay in the back? Microphone working okay? All right. Luigi, good to go? Okay, welcome. Thank you for coming. My name is Thiago da Silva, and this is Prashanth. We both work for Red Hat. At Red Hat, I'm a software engineer there, working primarily on Swift. Prashanth and I work primarily on Swift. I'm a core developer for the community. And we're going to be talking about what we have learned about Ceph, Gluster, and Swift. The reason we wanted to talk about that is because we find it pretty cool. I consider myself pretty lucky because even though I work on Swift, I sit right next to architects and developers for both Gluster and Ceph. So we share a lot of knowledge. We talk a lot about principles of distributed storage systems, and I find it very interesting, or we find very interesting, to see the problems that each one have, and they share a lot of the same principles, the same issues, and they come up with different solutions sometimes, or a lot of times they come up with even the same solutions for similar problems. So talking a little bit about those systems, of course they are all open source systems. They're in a way trying to achieve the same thing, which is scale out storage. These are systems that are trying to allow the flexibility of growing your storage system as your capacity grows, as your need grows. They can grow. They also are trying to prevent vendor lock-in and also to be run on commodity hardware. The interesting thing about these 3 different systems is that they're very successful projects. Each one of them are deployed massively across many different organizations. We hear about CERN running Ceph clusters. We hear about Facebook running Gluster clusters. We hear about, of course, Rackspace, who was the original author for Swift. The huge clusters that they have there. So all systems, all these different projects are very, very successful. They share a vibrant community. They've been around for a while. So it's very interesting to see that all three projects are running very, very well. Talking a little bit about the storage types that they support. Block, Ceph supports block and object. Today, they are working very hard on CephFS, which will bring in the support for file on Ceph. Gluster supports primarily file. That's what it was designed for at first. But it also, there are community members out there who also use it for block and object storage. Swift, on the other hand, was primarily designed for object storage, and it has no plans to support either block or file. So again, just talking a little bit about how similar or different they are. Prashanth's going to talk a little bit about the architecture of each one individually.
These three storage systems themselves are very complex and vast. So we'll try to have a crash course on each of these as quickly as possible. So starting with Ceph. This is how the Ceph storage stack looks like. At the bottom of the Ceph storage stack is the Rados object system. And it's a reliable, autonomous, distributed object store. So before we get into the object system itself, what is an object? What is comprised of an object? When I say object, what it really means is you have an ID, you have the data in the object, and also a metadata. And the ID is used to store and retrieve the object. The data is the actual content of the object. And in this case, metadata are key value pairs, which are attributes of the object. And on this stable, very cool object store, you have other layers built on top of it. For example, we have LibRados. So if you have a custom application with a specific use case that wants to talk directly with the Rados storage system, it could link with LibRados and store and retrieve objects in Ceph. You also have the Rados gateway, which is a HTTP server which provides a REST interface to the objects present in Ceph. And block interface is one of the most popular and widely used ways to consume storage. When you have VMs, Ceph can export a block device to the VM, and the VM can choose to attach it, format it with the file system, or if it has any applications that can directly talk block, it can directly consume the block device itself. And then we have CephFS, which is a distributed POSIX compliant file system. It's more like NFS, and it can be mounted and consumed in a VM or a client. So one difference in the way applications consume Rados directly and via Rados gateway is that Rados is more low-level access. So you can do things like store objects, partially update them. You can have compound operations on objects. You can get notified when objects get changed. But when you use Rados gateway, it provides a lot of additional feature sets, such as you can put objects and segregate them in terms of buckets. You can authenticate users and provide ACLs based on buckets. You can also set quota on buckets. So Rados gateway is more rich in terms of feature set. And also when you directly store objects over LibRados, so the object size is typically small. And what Rados gateway does is it allows you to stripe objects so that you can have really big objects when you store objects via Rados gateway. And if you have existing applications written in which talks to Amazon S3 API, you can just use them directly with Rados gateway. You just have to change the URL and point your application to Rados gateway instead. And it also supports the Swift API. So in terms of Swift's terminology, a bucket is a container. So if you are talking in terms of S3, you can put objects into buckets. If it's Swift API, you can put objects into containers. So let's go a little deeper into how the Redis object store itself looks like. So a Ceph cluster primarily has two kinds of daemons. So one is the OSDs themselves, and these are usually hundreds to thousands in numbers, and they take care of one disk usually. It can be a RAID group as well, and their primary purpose is to store objects and serve them to the clients. And when I say clients, it can refer to Libredo's application. A client can also be the RBD layer. It can also be CephFS. And OSDs are not passive devices. These are very intelligent, very cool devices, and they usually take care of replication in there. And they also make a note of other OSDs going down and report it to monitor. So monitors are the daemons that knows how the cluster looks like. It knows what OSDs are down, what nodes are down, what nodes are up, what devices are in the cluster, what devices are not. And its main purpose is to maintain the cluster membership and state. And it uses this algorithm called Paxos internally to vote and come to a consensus for things whichever for decision making. And monitors are deployed in small odd numbers because you usually need quorum when you have to put things to a vote. And if you have monitors in huge, large numbers, it takes longer to come to a consensus. If you deploy CephFS, there's an additional daemon that needs to be running. That's called MDS, metadata server. And what it does is it keeps track of all the file system metadata that's there. This is how the Redis cluster would look like. Now let's look into a brief introduction on how Ceph places data itself in the Redis cluster. So Ceph uses something called as the crush algorithm. So Ceph can store millions and billions of objects, and there should be some way to segregate these objects. And here, a Ceph cluster is divided into pools. So why pools? So there could be a use case where you need some set of objects replicated twice, some set of objects replicated thrice. So a good example is, let's say, you provide a system where you allow users to upload your images, and you need to store thumbnails. You may want to store images thrice for resiliency, but you don't really care about thumbnails. If you lose them, you can always regenerate them. You may want to store just one copy of the thumbnail. So that's where you can create two pools. One pool can store 3 copies, another can store 1. And also, as these clusters are huge and contains so many objects, it's so hard to keep track of where each object goes. So you group it into placement groups, and placement groups are a collection of objects, and these placement groups are mapped to OSDs. So by default, when you have 3 replicas, 3 OSD daemons are responsible to store and retrieve those objects. So here's an example on how crush determines where to store and place the objects. So crush uses the name, the identifier of the object itself, and the pool name to derive the placement group. And crush knows which OSDs are responsible to store objects that belong to that particular placement group. So there is a primary OSD that initially accepts the request from the clients and stores the data, which is eventually replicated to 2 other OSDs, and these are synchronous. So the OSDs give an ACK back to the client only after all 3 writes have been done. That's pretty much how Ceph manages data placement. Now let's look into how Gluster does it. So here you have a bunch of nodes, and all of them contain some bunch of disks. So Gluster has this terminology called as brick. So a brick is typically a disk or a mount point. And what Gluster does is it combines the capacities of these bricks spread across various nodes and presents those to the client as a single namespace. And the single namespace is called as volume. So volumes are made up of bricks. In this example, you have those blue bricks which form a replica set, and the brown ones also form a replica set. So just like in the Ceph stack, you have object store at the base. Here you have a robust GlusterFS file system, and on top of GlusterFS file system, you have various other access mechanisms such as Fuse, NFS, SMB, and also object-based access. Just like Ceph, Gluster also does not have a central metadata server. It does not have to look into a place or talk to a server to know where the files are. It can compute on a real-time basis. And just like Ceph, it also uses hashing to find where the data is. So you have the entire hash space divided into different ranges, and these ranges are assigned to bricks. And when you store an object, Gluster would know where to. When you store a file, Gluster would know where to place that file. So let's look at an example. Here I have 3 bricks of different sizes. 2 are of same sizes. And what Gluster does is it will assign a hash range to each of them depending on the size of the brick. So if a brick is bigger, it assigns a larger chunk of hash range so that more files would likely go into that brick. And then when you want to store a file or access a file, Gluster hashes the file name, and from the hash, it will know which brick to place the file in. And unlike other object store like Ceph and Swift, as GlusterFS is basically a file system which allows rename, their renames are handled in a specific way because when you change the file name, the hash changes. So when you rename a file, they create a special pointer file without moving the actual data immediately that points to the real location. And as and when you want to grow your cluster size, you add devices. And when you add devices, the existing data is moved to the new devices so that there's a uniform distribution again. Yep.
What if the hash is 41, but that brick is already full?
Gluster has logic there to move it to a next brick, but it can point to the original brick. So it has this logic of it's called a link to file. So
It's the same case as the rename, basically.
yeah, it's the same case as the rename. So GlusterFS by design is very modular, as in you can stack up different modules. And in the earlier example, you had seen bricks. Here, 2 bricks are combined as a replica set. And when the distribute module writes data, instead of writing to 1 brick, it will write to a replica set here. And the replication module in Gluster is responsible to provide high availability in case of failure. It follows a transaction model. Either it writes to both the replicas or does not write to both. And when one of the bricks or node is down, and when it comes back up, it has the capability to copy the new latest file and overwrite the old stale file in the other node. That's called self-healing. Yep, that's pretty much about how Gluster does it. Swift is in OpenStack. Yeah.
What happens when you have a failure in one of the bricks? What happens with the files inside that brick when that brick specifically fails? Yeah, and if you don't have the replication applied, you actually lose access to all the files inside the brick.
If it's just pure distribute, you do. If it's let's say the first brick goes down, and you don't have access to that, there's a configuration in Gluster where by default you can still write to the other brick the client still gets to do I/O on the other brick, and when the first brick comes back up, all the I/O that was done on the second brick is copied back to the first brick automatically. Does that answer your question?
Yeah, but for example, the files I have in the failed brick,
Yeah.
they will still be presented to the client, or
No.
the client will not see them in the global file system?
If you go on the back end, you can still access them, but it won't be presented.
Yeah, but I mean, clearly, if you make only one copy,
Yeah.
you lose that one copy, you
Yeah.
don't see them.
Yeah, yeah,
But if normally people have 2 copies or more.
yeah.
So where is that information stored? You're saying you're generating that hash that determines on which brick
Mhm.
you will
Mhm.
locate the file.
Mhm.
When I have 2 replicas, for example,
Mhm.
and the original one goes down, how do I determine where the replicas are?
Let's say the first brick is down now, and the client cannot access it. So all the IOs happen to the second brick. And when the second brick is doing IOs, it will mark that file saying that the other brick is down, and this file needs to be healed back when the other brick comes up.
But how do I find the upper brick? I mean, the next best one
Mhm.
necessarily have the file that I have. In Ceph, I understand this is the job of the monitor.
Mhm.
Node, what is it here?
So in the back end, so there's although there is no central metadata server, there are directories where the AFR module keeps track of files that needs to be healed. So
I think maybe it's a simpler question.
Yeah.
I think what he's asking is, when you define a volume,
Mhm.
you know what replica pairs are married together.
Mhm.
Right, that's static and that's fixed.
Yep.
If one goes down, you always know what who the second is. You don't have to heal to get at the objects in the replica pair because it's a static map that the clients know about.
So that's why it's so important to point out that it uses this hashing algorithm, this very deterministic hashing algorithm. So like Rick said, you have 2 replicas. One goes down. Your hashing algorithm for that file that is trying to store, it still points to that second brick. It will point to both bricks, right? One you can't get to, the other one you can get to, so you still have access to your data, which I think also answers.
I guess the answer is that during the monitoring of the remote file or remote storage, you get information on all replicas. So the client knows which replica are you handling the brick. Yeah? So with one brick down, you also still have 1 or 2 additional brick and can access.
Exactly.
yeah. Swift is purely an object store. In Swift, a cluster is logically divided into accounts, which contain containers, which eventually contain objects. So Swift contains 4 services or daemons running. One is proxy server, one is account server, container, and object servers. So the container servers keep track of what objects are stored in that container. The account servers, they keep track of what containers are stored in that account. And these are stored in backend as SQLite databases. And just like objects are replicated thrice by default, even the SQLite databases are replicated thrice. And a client to Swift can be any HTTP client. It could be your mobile phone, it could be a web browser. And the proxy server here acts as the single entry point to the cluster. So clients never talk to the backend node directly. All the traffic goes through the proxy, and the proxy knows how to route the request to the appropriate daemon or service in the backend. And for example, Wikipedia, all the images and thumbnails that you see in Wikipedia are stored in a Swift cluster, which is pretty cool. Yeah, so you can have a load balancer and multiple proxies. Just like Ceph has a crush map to know the map of the cluster, there's something called as ring in Swift, and these are internal data structures. So when I say a ring file, what an admin of the cluster does is he creates these ring files and pushes it out to every node so that every node has an idea of what the cluster is, what it looks like. So whenever you add devices or nodes, you need to recreate these ring files and push out to all nodes. And Swift also uses hashing without any central metadata server, no surprise there. So Swift divides the hash range into different partitions, and it pre-computes these two tables when you create the ring file. So here, when there is a request to create or retrieve an object, it will do a MD5 some hash of that object, and it will determine the partition. And each partition in this example is assigned to 3 devices, and then you have a table of devices, and Swift will know exactly that which object goes to which node. And when it creates these data structures and tables, so Swift has this replica dispersion algorithm that makes sure that the replica pairs are in different domains. So if, for example, if you have just one machine in your Swift cluster and 3 hard drives, it will make sure that the 3 replicas are in 3 hard drives. If you have a huge cluster, it will make sure that, let's say, the 3 replicas are in different racks. So Swift is very intelligent when it forms these ring files to make sure that the replicas are in different failure domains. That's about the architecture of these. Thiago will explain about further similarities and differences.
So yeah, hopefully you can keep it that. You're able to see some of the similarities already that they share. So for example, again, they all a scale-out system. They allow you to grow as your capacity grow. They're all using some kind of hashing algorithm to determine where your data is located in what disk. They're all trying to save your data in such a way that if you have failure, you don't lose your data. For that, they both up until now, there's primarily being using replication. More recently, all these systems are also introducing erasure coding. So looking a little bit deeper into the similarities of them, so we can see that in Ceph, the Ceph client speaks directly or talks directly to the OSD, as Prashanth mentioned, and you typically have a mapping of an OSD service to a disk, to a low-level disk, and the OSD disk is usually formatted with an XFS file system, because Ceph uses X headers on the file system to store metadata. The same is true for also Gluster and Swift. They all using the XFS file system at the very low level to store the data on disk. So in case of Ceph and Gluster, the client speaks directly to those underlying services. In case of Ceph OSD, in the case of Gluster, GlusterFS. In the case of Swift, you have the proxy communicating with the Swift object server, which in turn also uses the XFS file system to store the data there. Looking a little bit more in terms of how each system does redundancy and rebalancing, in Ceph, you can determine your replication or your redundancy level, granularity, at the pool level. So in a cluster, you can define several pools, and in each pool, you would determine, okay, I want this pool to have 3 replicas, I want this other pool to have 2 replicas, depending on your use case. In Gluster, you determine your redundancy at the volume level, and in Swift, you determine that at the container level. So you define what's called a storage policy, and when you create your container, you select what storage policy you want. In terms of where that data is placed across different failure domains, in Ceph, it's managed by the crush algorithm. and also in Swift is managed by the ranks like Prashanth talked about. So what Ceph and Swift allows you to do is to define your cluster topology. As you are first defining your cluster, you can provide what your topology looks like, your cluster topology looks like, and both Ceph and Swift will use its algorithms to place the data in as different failure domains so that you don't lose your data. Gluster differently, it's more of a manual effort by the admin. You have to know as you're defining your volume, you have to specify what disks to use for that volume, and the admin himself would have to know, for this disk, a disk is in this rack or this rack or this rack, so that they are placed in their own different failure domains. For that, Luis is going to save us, and he's actually working on a project. It's called Hackaday, that will automate that process in Gluster also, so that it automatically places or creates volumes in using disks in different failure domains. So that it's such not a manual process. He's going to be talking about that tomorrow. So there you go. Did your ad for you. In terms of both replicating data that has failed, as you guys were asking before, or rebalancing data. As you add more nodes, you need to rebalance the data. In Ceph, it will rebalance a whole placement group. So instead of, like Prashanth talked about, instead of rebalancing or moving one file at a time, trying to figure out what file to move, it rebalances a whole placement group. In Gluster, it actually rebalances or replicates individual files, and in Swift, it will rebalance or replicate partitions. So again, remember that placement groups and partitions are sort of the same idea of their ranges of your hashing algorithm. Just to understand a little bit more about how each one of the systems do replication, when a RDB or a LibreDOS client sends data to a Ceph cluster, it will communicate with one primary OSD. It will send data to that primary OSD, and that primary OSD is responsible for sending data to its secondary and tertiary OSDs. Those three OSDs, again, are in the same placement group. Once it gets the OK from those OSDs, it then returns to the client saying, OK, I have saved your data durably. Gluster does more of a fan out from the client itself. The client is responsible for speaking to the three different bricks. Again, I'm assuming here that it's a 3-replica system. Hopefully that was clear. But Gluster will communicate with 3 different bricks and send the data, will fan out the data from the client directly. So the client here is responsible for doing the replication. In the Swift case, you have the HTTP client sending the request to the proxy to put the data, for example, and the proxy is then responsible to fan out that data to the object servers, to 3 different object servers. What's the takeaway here is that all of these systems, they will only, they are responsible for storing your data in a very durable way. They will not respond to the client until you have some kind of quorum that your data has been saved. So for example, in the case of 3 replicas, at least 2 of these services, 2 of these replicas must have responded to the client or the proxy, in the case of Swift, that the data has been saved. Just to show a little bit more of similarities, in the case of Ceph RGW, one sec. Just to finish this thought. In the case of Ceph RGW, it's very similar to Swift, where you have an RGW gateway or a Rados gateway, and you have your HTTP client communicating with the Rados gateway, and the Rados gateway is responsible for storing the data. In the case of Gluster, for example, if you didn't use the Fuse client and you use an NFS, you would have an NFS server, and your NFS client communicates with NFS server, and the NFS server then is responsible for doing the replication for you. Yes?
You previous slide you were talking about how Gluster replicates files and he only replies to the client when the files are actually written. But in this case we're talking about synchronous I/O, right?
Yes.
Correct.
And how about async? Is there something special about async or is just
Async would be the same way, right? You will not return back the synchronous write on the I/O submit. Once it writes it, the submit will come back once it's written. So it will just come to you asynchronous.
Thank you. Does that answer? So we just wanted to show really quick how does your data look like in the underlying file system. So in the case of Ceph, Ceph provides some tools for you to use, communicate directly with RADOS and put your data using RADOS tools, and then look up where your data is in the cluster. So you can see that Ceph, like Prashanth talked about, it actually breaks up into small objects. It's not very human readable, so you would have to go searching for it. Basically, you'd have to use some kind of tool to go look for it. In the case of Gluster, the directory structure, the file directory structure, maps directly to how the data is stored on the brick. And in the case of Swift, Swift actually takes your URL key and it takes the end of that key there and hashes, and it stores the file with that hash name. So it's not human readable at all. It would be very difficult to go find that data on the underlying file system.
Does it tag the file in metadata or something, the actual file name?
Yeah, so all three systems, they use X-adders to store a whole bunch of data. So yeah, it stores the file name, for example, there. In the case of Swift, you also have, and actually in the case of object storage in Ceph, it also uses the container database to also store some metadata about the object being stored. Terms, again, just very quickly talking about some feature parity. They all support some kind of quota. Ceph supports quota at the pool level. Gluster at the volume level, also directory and inode counts, and Swift at the account and container level. They all, both Ceph and Gluster support tiering. That's sort of new features for them. Swift does not have a tiering feature yet. In terms of geo-replication, being able to replicate to faraway data centers with higher latency, Ceph and Gluster have a active-passive or a master-slave geo-replication, but Swift provides a active-active replication where you can write and read your data from both data centers. Like we talked about before, they all support now erasure coding and also bit rot detection. As data sits there on disk for a long time, you want to be able to detect bit rot. And that's all we got. We had a bunch of questions already. Any more questions? We got about 5 minutes or less. Yes?
I would like to ask you, how is Gluster able to cope with the replication? Because we are using the Ceph, and during backfills, it makes huge peaks on the network, so it can affect the client.
Yeah, no, I mean, so you're talking about like how does it replicate data on a failure?
Yeah, or whether I'm able to limit the bandwidth used for the replication. When one bit just go down and the replication starts, then I don't want to use the whole bandwidth for the replication.
Yeah. Oh boy, I know. For example, Swift uses a. It allows you to use a different network just for replication, exactly to limit that. I'm not 100% sure Gluster if Gluster supports that or not. So it would happen on the same network as the data path.
Because we use the maximum backfill, and we limit just one placement group at a time to make a replication. It's quite okay.
Yeah, no, absolutely.
Do you mean if there's any throttling? I think it's coming up. So as of now, all the cell fields are not throttled. They're adding the feature to throttle the bandwidth.
You get a scarf, by the way. Dispersion rules in Gluster. Right now, I know they have AFR, and I know they're talking about using NSR, which is been talked about for a while, and also.
So they use erasure coding in disperse volumes to store to split data into code in the data into parity and two types of chunks, and that's a pretty new feature.
Yeah.
They use erasure coding.
And striping too. I think it's been talked about for a while. Almost.
How is Gluster and Ceph with InfiniBand?
I know Gluster supports InfiniBand, and Ceph, I'm looking. Ilya, no, not. It's work in progress. Sorry that I'm not expert on Gluster or Ceph, as you guys can tell, more on Swift side, but I know Gluster supports InfiniBand. Ceph is a work in progress.
We test InfiniBand on both, and there's companies like Mellanox that care about InfiniBand that work on Gluster and Ceph both. So,
Okay. I think we're out of time. I've just been told, I'm sorry. But thank you very much. Let's see if I can remember who.
I think if you have any further questions, you can catch the guys outside.
Oh, sorry.
Scarf? How it is Ceph
Recover mine.
Hey.
Hello. So just 1 minute.
Yeah, sure.
So how are you?
Okay, so now is updating live OpenStack Cloud. Free guys.
No, we have a video. Okay. So we can't do a demo of that. We don't have enough time. Yeah, this is what he was asking. Do we have to like the whole new one? Okay, you can start with wearable one.
Alright, so I think this is your laptop?
No, this is.
So the guy laptop?
Moja prezentacja.
Ja wiem, ja czekałem tam na górę.
So to us it's like quite a lot.
It's like a game.
Like a game. We need to challenge it. We don't use all the problems
We have 2 mics, but I think you can just pass it.
Yeah, I think we can pass the board. It's gonna be interesting presentation. Can we hook up?
Because
of the mics?
VGA.
Because of the title.
So same laptop, but at least you don't need to switch the laptop, right? And the slides.
Yeah, same laptop.
Same slides, okay.
Yeah.
No, that's at least something. Let's start.
So I need to mirror it?
Yes.
And tell Thiago.
Tell him to put the presentation.
No, just don't fall down. It's a step. It's invisible. Just happens. Okay?
No, I can't.
Is it okay? As long as I have on the... Yes? Oh, yeah, it's interactive. Yeah, can I put the...